Welcome, we are from Group 7 of OCC2 and our title is Refrigerator Temperature Control System. Our teammates are KIG3012, Chu Qixuan, Ding Minghan, Qi Xiongyu, and Teo Zijing.
In this project, we aim to address key issues found in typical refrigerator temperature control systems. Many current systems struggle with maintaining a stable internal temperature due to poor adaptability. This not only leads to spoiled food, but also causes higher energy usage and a poor experience for users. The core technical challenge is the lack of dynamic response to environmental changes. The main goal of our project is to create an intelligent temperature control system for a refrigerator. Our system can adjust cooling automatically based on both internal temperature and external conditions like room temperature. This helps to keep food fresh longer, save energy, and reduce environmental impact by using a more efficient and responsive control method.
Next, we'll talk about our model and block diagram. As you can see, at the left-hand side is our model, and at the right-hand side is our block diagram. First of all, our control knob will send an input to our mechanical thermostats, and our mechanical thermostats will send input signal to our microcontroller, which will after that send signal to our cooling coil, heat generator, and make output to our temperature in refrigerator. Then our temperature in refrigerator will send a feedback to our temperature sensor, which also send a feedback back to our microcontroller. Before our calculation, we have to do some assumption of our model. First is our refrigerator. We assume that the rated current is at 5 ampere and the rated voltage is at 220 volt, and the volume is assumed to be 150 liter. Next will be our control knob. We assume that the maximum rotation angle is at 180 degree, and we'll set the highest temperature setting, which is 5 degrees Celsius at angle of 0 degree, which the output voltage is 0 volt. And also the lowest temperature setting at 1 degree Celsius at an angle of 180 degree, which the output is 220 volt. By setting the temperature like this, we'll get a linearly proportional to the rotation of the knob. Next is our evaporator. We'll assume that the efficiency of the cooler is 100% and the material of the capillary tube is copper, and the capillary tube length is 5 meter with an outer diameter of 0.1 meter. Next, we'll move on to our mathematical model. First of all, we'll talk about our control knob. We know that the sensitivity of the knob K is equal to the maximum voltage minus the minimum voltage divided by the maximum temperature minus the minimum temperature, and we'll get 55 volt per degree Celsius. Therefore, the voltage output is equals to KT. After having a Laplace transform, we'll get G1 equals to V out over T in, which is equals to 55. Next, we'll move to our evaporator. We know that QT is equals to MCP dt, and the Q internal loss is equals to the Q evaporator gain. Therefore, we'll equate two equations together and we'll get MCPT is equals to IV. After doing Laplace transform, we'll get G2 equals to 1 over MCPS. By having the assumption before, the length of the capillary tube is 5 meter with outer diameter of 0.1 meter, and the properties of the solid copper metal with density of 8,960 kilogram per meter cube and a specific capacity at 0.385 joule per gram degree Celsius, we'll get G2S equals to 5 over 135,465.475 S. Next, we'll move to the heat generated in refrigerator. We know that Q is equals to MC over dt, which is equals to V density Cp dt over dt. The rate of heat transfer governed by the thermal resistance R of the medium and air. Therefore, Q is equals to T2 minus T1 over R. And by substituting Q, MCP dt over dt is equals to T2 minus T3 over R. After the Laplace transform, you'll get G3S is equals to 1 over 1 plus R multiplied by V multiplied by density multiplied by our specific capacity multiplied by S. The volume of the refrigerator V is also known as 150 liter or 0.15 meter cube, and the thermal conductivity R, the density, the specific heat capacity of the air is at 50 degrees Celsius, which is having a thermal conductivity of 0.02476, the density of 1.225, and the specific heat capacity at 1007 joule per kg Kelvin. By substituting all this value, which obtained from the thermodynamic table, we'll get our G3S is equals to 1 over 1 plus 4.5815 S. Next, by having all of our G, we can move forward to our reduction of multiple subsystems. From our block diagram, we'll input all our equations as the blocks in our block diagram to show a multiple subsystem. First of all, we'll reduce the series of G2 and G3 by multiplying them as they are connected in series. Then we'll reduce the feedback sensor together with the block above, which is our G2 times G3, and we'll get a straight open loop, but we still have our potentiometer Therefore, we'll combine our potentiometer and our G block together to make a single input, single output, and one equation open loop system. Then we'll create a unity feedback system so that we can do our steady state error monitoring.
So here are the codes for this system. I have separated it into a few sections, mainly which is uncompensated system using manual calculation, which we calculate it manually, and compensated system using CISO design tool. And I have also included the step response, comparison, and pole zero plots. Over here, I have added the steady state error analysis and stability check using Roth-Hurwitz. And here are the MATLAB results for pole zero plot, step response, and pole zero map. From the step response, we can find that the rise time is 1.07 to the power of 3 seconds, while the settling time is 1.91 to the power of 3 seconds.
Here's a quick summary of our performance metric. The uncompensated system has a rise time of 1070 seconds and a settling time of 1910 seconds, with no defined overshoot or peak time. With our manual compensator, rise time drops to 11.3 seconds, settling time to 33.4 seconds, overshoot is 6.4%, and peak time is 23 seconds. The single input, single output tool design further reduces the rise time to 9.76 seconds, settling time to 31 seconds, and keeps the overshoot under 10% with a 20.5% peak time. On this plot, the blue curve is the uncompensated system, the red is our manual design, and the green is a single input, single output tool design. Notice how both compensator transform a nearly flat 1900 seconds response into a rapid 30 second settlement, all while keeping the overshoot below 10%. From the results, we can see that the setting time has been shortened by around 98%, from 1910 seconds to around 31 seconds. The rise time has dropped dramatically from 1070 seconds to under 10 seconds. The overshoot is controlled below 10%, meeting our design goal. The steady state error for the step input is virtually zero, and both manual and single input, single output designs meets our specification, with the single input, single output tool slightly faster. In summary, our controller turns an impractically slow system into one that stabilizes in under 35 seconds with minimal overshoot and fully satisfying all design requirements.
In a conclusion, this project successfully designed and analyzed a refrigerator temperature control system with the goal of improving temperature stability and energy efficiency. After establishing a detailed mathematical model and conducting time response stat and stability analysis, the system was confirmed to be overdamp and stable. The most significant findings came from the results and discussion section, where a performance comparison between the uncompensated system, the manually compensated system, and the seesaw design tool compensated system was presented. The uncompensated system showed extremely poor performance with a settling time of 1910 seconds, far exceeding acceptable limits. In contrast, both compensated systems achieved dramatic improvements. The manually compensated system achieved a settling time of 33.4 seconds and an overshoot of 9.4%. The Seesaw Design Tool compensated system further optimized the response with a settling time of 31.04 seconds and overshoot of 9.57%. Both methods successfully met the design specifications of settling time less than 35 seconds and overshoot less than 10%, validating the effectiveness of the compensation strategies. While the manually designed controller offer better overshoot control, the Seesaw tool proved to be more efficient for iterative tuning and visualizations. These results confirm that a properly compensated control system can significantly enhance the performance of refrigerators, temperatures, regulations, aligning with the project's objectives of improved precision and energy savings. Future work may focus on real-time implementations and further optimization through the adaptive or intelligent control techniques.
That's all from us. Thank you.